All right, so good afternoon, everyone. Let me share my screen quickly. Yeah, welcome to the lecture number 8. This is very important lecture for the entire course. We're gonna discuss this. Well, we will focus on golden quantum circuits, single qubit and 2-qubit golden quantum circuits, and we will learn in more detail this Qiskit IBM library software for simulation quantum computers. And today we're gonna create a quantum circuit and send to a real quantum computer for quantum simulation. All right, but before we start this one, let us quickly go through the previous lecture 7, which which I taught on last week, and that was the spring break, so not much of you attended that lecture. So let me go through this one so we are on the same page. Okay, so last week we discussed single and 2-qubit quantum gates, okay, and how we can compose the quantum gates to build up quantum circuit. Alright, so here I encourage you to watch this lecture 6 and 7 from my old quantum computer course without much of Python, where we derived all these formulas and discussed maybe in more detail the concepts. So I encourage you to watch those, especially part about the quantum gates anyway. So let me import these libraries in case I need them. Alright, so we introduced this block sphere last time, and we discussed how we can represent any state of a single qubit as a point, as a dot on the surface of such a block sphere. Okay, so the block sphere looks like this. It gets north and south pole, and it turns out that the north pole corresponds to the 0 state of a qubit, and the south pole corresponds to state 1 of a qubit. And then we also derive the positions of other important fundamental states of a single qubit, including the states plus and minus, which are located at the axis x. So this point here is the plus state. This opposite point on the axis x is the minus state. And likewise the states plus I minus I, which are represented by this point here on the axis y. So this is plus I state and opposite minus I state. Alright, so we use this block sphere to represent the state of one single qubit. And of course, quantum computer requires much more qubits than just one, right? So we need something else to represent the state of a multi-qubit system. And we will discuss this representation today. So last week we discussed quickly about classical quantum circuits and quantum gates versus quantum. Okay, so here is a brief reminder on classical logic gates. Gate NOT, XOR. We discussed that, for example, XOR is irreversible, so it's not reversible, right? And this point of irreversibility in quantum computing actually was a problem, because irreversibility in time means dissipation because of the second law of thermodynamics, right? And some time ago, people actually thought that since the classical computation machine is built on these irreversible logic gates, the machine cannot be large enough to compute useful things, because since it's a dissipative machine, it cannot be too large. Yeah, so even like several decades ago, people thought that we won't have personal classical computers. Today, we have them in any pocket, right? Any cell phone is a personal computer. Some people today believe that we won't build the quantum computer which is useful enough because of some also pitfalls that are considered to be fundamental, but the vast majority of the quantum engineers agree that at some time, in the future, we will get the large enough quantum computer. Anyway, so combining classical gates together, we can achieve like interesting functionality. For example, this is a circuit of typical adder, right? The structure, the circuit that can compute, basically, to sum up or subtract logical bytes, logical strings. And so then we came to the quantum circuit. And this is a typical example, like one example of a quantum circuit. So it looks like this. Each line here corresponds to different qubit, okay, in a system of qubits. So this particular circuit is 5, right? 5 qubit system, because we numerate them from 0 up to 4. So 5 qubit system. Each very important difference between quantum circuits like this and the classical circuit like this one is the fact that the classical circuit is the special structure. So it composed of physical logic elements distributed over some chip. Okay, and these black lines correspond to some wires that connect the gates on the chip. In drastic contrast to quantum, where these qubits represented by physical objects, but all these gates are not physical. They are stimuli. They are some pulses. These are just the way we interact with the qubit. So these black lines here are not physical, right? So it's a temporal circuit. This is spatial circuit in space. This is the temporal circuit in time, okay? And and this is just one particular example of a real quantum processor with 133 qubits. It's called IBM Torino. There are some, this note is basically discussion about this difference between classical and quantum circuits. So in this topology, each circle is different qubit, and then these qubits are connected with their neighbors to provide the tunable entanglement, tunable coupling, tunable entanglement between the qubits. But you cannot find the gates on this circuit, because gates, as I said, like stimuli, for example, like some microwave pulses that you send to the circuit, okay? And then we discussed different gates. If you didn't read this part, I really encourage you to go through the rest of this lecture. So here I put basic information about single qubit gates and 2 qubit gates. So single qubit gates are gates with one input, one output, and it acts on a single qubit, right? For example, these Pauli matrices, Pauli X, Pauli Y, Pauli Z matrices, they are typical examples of single qubit gates. And what they basically do, they rotate the state of a quantum system around the corresponding axis. For example, this Pauli Y gate rotates the state of a quantum system over this Y axis. Do I have a blocks here, right? So this is axis Y over here, and the gate Y rotates the state, this arrow, this red arrow, around axis Y. Likewise, the Pauli matrix Y or gate Y, X rotates around X, and Z rotates around Z. Very good. And a very important gate is Hadamard gate, okay, named after this scientist, Hadamard. So Hadamard gate, why it's so important, right? It's important because Hadamard gate creates a superposition of states. So it's still single qubit gate, so it acts on one single qubit. And let's say if my single qubit initially in the state 0, in this ground state, okay, if I apply this Hadamard gate on this qubit, it creates the superposition, 0 state plus state 1, normalized in an appropriate way to get probability 1. Okay, and if it acts on the state 1, it creates also superposition, but anti-superposition, right? So this minus here, superposition, anti-superposition, and that's very important for many quantum algorithms, like Groover search algorithm. This minus is extremely important. This minus basically allows to search for elements much faster than classical algorithms. Anyway, so another important single qubit gate is a P gate or phase gate, and what it does, it basically rotates the phase of a qubit. So let's say you have this state psi, which is alpha 0 plus beta 1. If you apply this P gate on this general qubit state, you get this phase factor here. So this phase factor creates the phase difference between the qubit states, and it can control the interference between them. Today we will use this fact for the single golden qubit circuit, which is called Ramsey interferometer. We will discuss today. Other phase qubits, and finally two qubit gates. For today we will need this CNOT gate or control NOT gate. This is a gate with 2 qubits input and 2 qubits output, okay? And this upper one, this black dot, bold black dot, is a it's control qubit, and this circle with a plus plus in it is a target qubit, okay? And the state of this target qubit depends on the state of the control qubit, namely the truth table. I don't have truth table here. Anyway, so the truth table is pretty much the same as the truth table of the XOR gate like this. So basically control X qubit, if the state of the control is 0, then this target qubit doesn't change the then this gate doesn't change the state of the target qubit. So if you have 0 in input, like here, so this is control, this is target. So if control is 0, then target leaves unchanged. It was 0, it stays 0. If it was 1, it stays 1. However, if the control is 1, the target is flipped. It's if it was 0, it became 1. If it was 1, it became 0. So it is a gate that is controlled by the state of the control qubit here. Okay. Of course, all these qubits, all these gates are unitary and hence reversible. Okay. So let's say if you have a circuit like this, and if you run this circuit from left to right and you get some result, if you get this result and run it backward from right to left, you will get exactly the states of these initial qubits. So the circuit is reversible. Of course, in the perfect case, in a perfect quantum computer, for a real quantum computer, this will change the result, and the degree of this change, this effect of direction, can be used as a benchmark to characterize the quality of a quantum computer. All right, and other quantum gates. So yeah, I encourage you to read through this. I mean, you will definitely read this material because your third homework is all based on this information. Anyway, so yeah, people still arrive. Let me transit to lecture number 8 now. Well, today I think it's gonna be pretty short comparing to others, and less theoretical. Okay, less informative, but very technical. And the material of this lecture 8 is this is the way you will do your lab work, so that's why it's so important. Again, I encourage you to watch a video from my old quantum computer course, where I probably discuss some of these things in more detail. However, yeah, I will return to this point in a second. So again, we import the important libraries and make available, this activate the multi-output. Yeah, and so Qiskit, right? Qiskit is a free open source Python based library, right? The Python software that allows you to simulate quantum circuits. Okay, so it's specifically for quantum circuits. Say you cannot simulate some quantum other systems like hydrogen atom or something. So this one is specifically for quantum circuits. You can simulate quantum circuits on your device, on your laptop, desktop, using some inbuilt quantum simulators. Okay, some other quantum simulators that mimic the operation of a quantum computer, also available through the cloud remote simulation through the IBM backend. Okay, so you submit a job to the external IBM some machine or virtual machine, and that machine simulates the project for you. This is second type of the typical projects that you can do using Qiskit. And finally, using Qiskit, you can submit your project to be simulated on a real quantum computer with different number of qubits. So there are 3 ways to simulate things using Qiskit: on your laptop, externally but using virtual machine, and externally using a quantum computer. So to get yourself familiar with this Qiskit, I encourage you to visit their website. Here, let me, for example, go to their website. Yeah, so this is the website of IBM Quantum Qiskit. Don't use this installation codes for the reason I'm gonna discuss in a few minutes. And in general, it's very useful platform. I encourage you to go to this information pages. You can read more about technology. More about IBM Quantum as a company, more about their technologies, research, and this learning is very, very nice. So this is alternative way to learn this IBM Quantum, not only IBM Quantum, but in general quantum simulations, quantum computing, and yeah. So my opinion that this platform is one of the most useful in quantum today. So yeah, Qiskit is an open source. As I said, you can find Qiskit on GitHub, and even install it from GitHub. Read more about the versions of different Qiskits. What's the difference between versions? Here you also go to their YouTube channel, right? Some of you, of course, already subscribe to their Qiskit YouTube channel. Very nice source of information about quantum. So here, for example, we immediately see this video by Emmanuel Bloch, which is, by the way, this Bloch sphere, right? So the Bloch sphere is named after Bloch, if I'm not mistaken. Yeah, supposed to be like this. Anyways, yeah, a lot of information. Recently, I also saw a video about job market search, how to find a job in quantum. So very, very interesting platform. Anyways, and yeah, and for this quantum simulations using IBM Quantum, you have to register in their system, this IBM Quantum, and get IBM ID and IP token. Okay, so you use this IP token to run a simulation on a external computer. So let me go to their website. Yeah, I'm already in. Let me sign out. Yeah, so this is what you see when you get to their website. You just click here, this create IBM ID, and then follow the registration procedure. And I suggest, or I recommend you to use your fiu.edu email account. All right, so register in the system because you will do your lab work in this IBM system. Okay. Choose a method. So what's going on here? Send me code. Yeah, interesting. Okay. All right. So the first step probably will be Qiskit installation, and before it was pretty straightforward. I just recommend students, you do pip install Qiskit, pip install Qiskit Air, and probably, yeah, this Qiskit pip install Qiskit IBM provider. This is how it worked in the past. However, when I tried to run the simulations recently, I've got a problem because recently IBM improved their Qiskit from 0.80 something, 86, up to 1.0.2. So the last version of Qiskit is Qiskit 1.0.2, something like that. And unfortunately, they didn't fix so they changed the language. They changed this library Qiskit pretty significantly, and that change caused a lot of mismatch between Qiskit and other libraries, including Qiskit Terra. And you used Qiskit Terra and Qiskit IBM provider to send your projects to IBM. And I spent some time to figure out how to solve this problem. And to read more about this problem, you can go to this link and read about installation of Qiskit 1.0. And as usual in these cases, they recommend to create a virtual environment and then installing part of the Qiskit in your base environment, another part of Qiskit, this Qiskit Terra in another environment, so you can use both. But I expect that will get a lot of problems. That's why I downgraded my Qiskit to the version that works properly with other Qiskit libraries. Okay, and here what I did. So it worked well from my home computer, but I didn't run it from my office computer for a while, and today I checked and it failed, and then I check what Qiskit libraries installed, right? So you basically use this pip list find str Qiskit, and this is the result. So in my case, it was Qiskit 1.0.1. So at some point it was updated, for some reason updated to a new version. Okay, and this caused a problem because this Qiskit 1010 doesn't work with Qiskit Air 0.13. Okay, so that's why I did the following. I removed all the Qiskit libs. I installed Qiskit, uninstalled Qiskit Air, and install Qiskit IBM provider, so basically removed all of them and then installed. So I struggled with this and tried several ways and several versions, right? And this one worked out. So now I use this environment, and I suggest that you use the same. So basically you need to install Qiskit of 0.46 version, okay? Then Qiskit Air of this version 0.13.2. And pip install Qiskit IBM provider 0.8.0. In this way it works. It works just great. And I really hope that they will upgrade this Qiskit Air soon, so we will be able to use Qiskit 1.0. I mean, this version 1. Anyway, so yeah, I installed everything, and now it works for me well. And here is the structure of like typical workflow of using Qiskit. Okay, so first of all, you need to create or announce. You need to announce a circuit, the quantum circuit, and it is done by calling this function quantum circuit, which is important from Qiskit, this line here. From Qiskit import quantum circuit along with quantum register and classical register. So you announce this circuit, and I give it a name circuit. Okay. Let me run this one. So for now, if I draw this circuit dot draw, this circuit is empty. The circuit is empty, doesn't have any gates, etc. Just 3 qubits. And 3 qubits because it's 3 here in parentheses. Okay. So then I add quantum gates. I just type the name of the circuit and dot and the name of the gate. So X is Pauli X, Y is Pauli Y, Z is Pauli Z, H small is the Hadamard gate, okay, and this CX is the control X or C naught gate from the previous lecture. And please note that all gates are in the lowercase writing. So you add these gates, and then you need to visualize them. So visualize is done through this function draw. So name of the circuit dot draw parentheses. It returns this quantum circuit. Of course, this is not nice representation of the circuit. That's why you can use some attributes here, for example MPL, to get your circuit look much nicer comparing. So this is exactly the same circuits, but this one is much nicer. And there was a red note here which says that they also gonna change this MPL to a new basically name in the new version of Qiskit. So this quantum computing area develops so fast, so you need to be on track and maybe update this software periodically. And on the the problem with this is that this sometimes causes this mismatching between the different libraries, as we just discussed. So I took this information from Qiskit tutorial basically. So it basically says that in contrast to other platforms, including SymPy quantum, right? The one we used to use in the until the previous lecture. SymPy quantum, in contrast to these platforms, Qiskit enumerates qubits from top to bottom. Okay, so it runs from first qubit here, then second, then third. Also from left to right, but also writing is different. So, for example, if qubit 0 in state 0, qubit 1 in state 1, and qubit 2 in state 1, Qiskit represented this way. So qubit 0 in state 0, qubit 1 in state 0. So this is qubit 0, this is qubit 1, this is qubit 2. So you add new qubits to this vector like from right to left. Okay, so the next new qubit will be placed here on the left. So this is the difference between Qiskit's representation of vectors and other platforms. And as a result, for example, if you compare this matrix for the control X, this one C0, you see this matrix. This is unitary submatrix, and this is submatrix. This submatrix corresponds to Pauli X. This is what makes this control X matrix. So if you compare this one in a traditional form and this one, so this is also control X, but in the Qiskit form, you will see this difference, right? So matrices are also different, but typically it doesn't cause any problems. All right. So how we simulate circuits? So as I mentioned already, there are 3 ways of simulating things using Qiskit. One way is just to run simulation on your machine, and to do so we use I will come to this point, so maybe I'm raising this point a little bit earlier. But anyway, so this is basically this part about simulating. So simulating. To simulate a circuit on your machine, on your system, you need to state the initial state, basically the state of your qubits in the initial state, right? This leftmost part. So this states of the initial states of all qubits. So you need to initiate that state. Of course, in reality, in real quantum computers, these states are always prepared initially in the state 0. So all qubits are in 0 state. That's dictated by the principles of minimum of energy and the fact that any system decays to the ground state. That's why typically quantum computers start from the 0 state. But on your machine simulation, on your computer simulation, you can start from any state here. So here I create the initial state vector, this function state vector, then dot from initial, and here we have this 0. It is the name of the state of a qubit in the integer representation. integer representation. Let me return quickly to the lecture 7. Maybe actually not 7 but 6. Let me erase lecture number 6 so I clarify what I mean by that. Integer. Here. Yeah, so this was in the end of the lecture number 6. So the point is that a qubit, for example, a qubit like this, right? So this is a state of a 3-qubit system, 1, 2, 3. So it's 3 qubits here, and this is a particular eigenstate of such a system of 3 qubits, 1, 0, 1. And if you convert this 1, 0, 1 into integer form, you will get 5. Okay, so you can write the name of the qubit in the 0, 1 format, like this logic string, right? 1, 0, 1, 0, 0, 1, and so on. Or you can write the same qubit using the integer representation. You just put 5 here. So it's basically the same state of a 3-qubit system, but one is in the digital format, another one in the integer format. Okay, so would it work? I'm not sure. No, because I need to import other libraries. Represent. Anyways, so these are two different forms to write the state of a multi-qubit system. Another. Let me quickly import these libraries so I get my point. My point, and this one too. Right. Yeah. So completely identical vectors. This one and this one, they are the same states of 3-qubit system. Okay. By the way, 3 qubits means the number of these coefficients, right? Elements, vector elements, will be 2 to the power of 3. 8. Another point, and you by the way have this problem in your homework. There is a question asking like, suppose you have a state 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, and so on. How many ones, how many units are in such a state? Okay, so I noticed that this problem, I mean, caused some such a problem caused some problem with understanding of this concept. So the unit is just one, because this number basically tells us the integer number of position of a qubit in state 1. That's it. So if I run like this, so this this vector will be very large, but all of them will be just zeros, except for one unit somewhere. Yeah, here, this one. And the position of this unit is given by the integer number of this digit here. Okay, so this number here we return to the state vector of the Qiskit, right? So this is the integer number of the state. Okay, so for example, if we have system of 3 qubits, 2 to the power of 3 is 8, and I can change this number from 0 to 7 to generate any of the basis vector. All right, and then what I do, I just to evolve the circuit on your machine, right? You just type .evolve and name of your circuit. So our circuit is named circ. This is the name of our circuit. State is the initial state, right? And then state.evolve and the name of our circuit. And as a result of this, we get a state in the final state of our circuit, which on the rightmost side of the circuit here. Okay, so the state of this circuit on the right side will be the result of this execution of the string state.evolve circuit, and we can represent, we can write down this state, and here is the result. Why I have a result like this? Let me see. Because I start from 0 state. If I change this state and run it again, I will get this new state. If I start from state 2, again in the integer representation, I will get a new state, and so on. For the state 3, I get new. For the state 7, I get a new one. So all these results are different. And of course, if I type 8 here, I will get a problem, because I have only 8 from 0 to 7 different amplitudes, right, of possible initial states. Okay, so in some sense, this part represents the functionality of SymPy Quantum. Okay, in there we also can draw the circuit, initiate the initial state, and compute the final state. So all this can be done in quantum in SymPy Quantum. However, Qiskit is much more than just these simple quantum computations on your machine. The same state can be represented in a matrix form. To do so, you need to import this array to LaTeX function, and using this function you can represent the state. If you remember, in SymPy Quantum we did the same using this represent function. All right, so this brings us to the important concept of 2-qubit golden quantum circuit and its simulation using Qiskit. Okay. So this is the result. This is basically what I mean by 2-qubit golden quantum circuit. As you can see, it's very, very simple, tiny thing. It consists of 2 qubits, 0 and 1. Using Hadamard gate, we create a superposition of the first qubit into state 0 plus 1. You remember the superposition, so Hadamard gate creates superposition. And this superposition, and by the way, we always start from, I mean, not always, in this case. So in this case, we start from state 0, which means 0 here, 0 here. Both qubits are initially in the state 0. So the Hadamard gate creates 0 plus 1, and this superposition of 0 and 1 affects the state of the controls, the state of the second qubit, through this C0 gate here, okay? So superposition of qubit 0 in a 0 and 1 state controls the state of the second, of this target qubit. And yeah, so in order to draw this circuit, I again create the quantum circuit, add the Hadamard gate, add CX gate, and draw this circuit using this MPL representation. I send the state 0, which is 0, 0 in the binary form 0, 0, and I calculate the output, this final state, and represent them using LaTeX. So this is the result. This is the circuit. This is the input state 0, 0, and this is the output state. So here at this point, you must recognize this Bell state, right? This 0, 0 plus 1, 1, the Bell state. We discussed this, I guess, also in lecture number 6. Yeah, here, Bell states. I refer to this part, Bell states. So Bell states are perfectly, totally entangled states of two qubits. Okay, so the purpose of this golden qubit circuit is to generate a Bell state from two initially uncoupled qubits. Okay. Yeah, so this is the purpose, and if you change this initial state, we have this freedom to change the initial state, for example, to the state 0, 1, and run the circuit again. 0, 1 input, this is the output. You see, this is a second Bell state, 0, 0 minus 1, 1. If you go here, 0, 0 minus 1, 1. This is the second Bell state. If I change the initial state to state 1, 0, 1, 0, it is state 0, 1, 1, 0. Another, the third Bell state. And finally, for the last third state, which is 1, 1, I again generate the Bell state, which is fourth Bell state. All these states are totally, perfectly entangled. Okay, and I just remind you what it means, this entanglement, quantum entanglement. We discussed that, but I remind you. So in the input of this circuit, in this particular state 0, 0, we get this output here, 0, 0 plus 1, 1. This state is how's it? You cannot write this state, I forgot the word, separable, right? Non-separable. So this state non-separable, which means that you cannot write this state as a product, as a tensor product of two states of two qubits, because if you would have state 0 here, 0 here, the tensor product is this one, 0, 0. If this one would be state 0 plus state 1, and this one is state 0, then you will get state 0, 1 plus state 1, 1. Again, can be represented as a product of two states. This one cannot be represented as a product of two states, and this state is entangled. And now, if you measure, for example, qubit 1, this qubit 0, okay, this upper qubit, and let's say you find this qubit in this, so you can find this qubit in the state 0. The first one is here, this one is 0 or is 1. with 50% probability, okay? And let's say I find this first qubit in the state 1. According to the principles of quantum mechanics, you remember this collapse of the quantum state, right? The entire quantum state collapses to this term, this vector here, 1, 1. Which means that if I measure the second qubit, this Q1 qubit, it will be with 100% certainty will be presented in the state 1 after the experiment. So the action, like this measurement that I do for the qubit 0 affects the probability distribution of the qubit 1. Okay, in some sense, it's like affecting qubit 0 immediately affects the qubit 1, regardless of, for example, physical distance between these two qubits. And this is the result of the experiment, like of many experiments today. If you create such a Bell state superposition, and then you divide these two particles like very far away, a few miles or billions of miles, measuring one qubit immediately affects the state of the second qubit. Okay, so sometimes it's called quantum non-locality, quantum non-locality. This is what Einstein called spooky action over distance, something like that. So people were very afraid about this fact, because it sounds like we can send information faster than the speed of light, but it turns out that it's not possible to send information using this principle. So our physics is completely fine, and still we can use this effect, this quantum entanglement, for many very important things, including quantum cryptography, which is the technology of our use today. We already use this quantum cryptography for secure communications, and quantum computing, which is another emerging very promising platform, very promising application area. All right, so we can simulate a circuit, get the final result. How we can represent the state of this system? So you remember when we discussed this Bloch sphere, I particularly underlined that this is a way to represent a single qubit system. So Bloch sphere works for a single qubit. If you have a system of two qubits like this one, you cannot represent the state using Bloch sphere. That's why people fought a little bit and figured out this approach of Q-sphere. Okay, so IBM uses this Q-sphere approach to represent the state of a circuit. And you can read about, how it's done exactly. I spent some time and wrote this part. Basically, this Q-sphere looks like this. It's also a sphere, but it also supplied by this phase distribution, okay, phase, which is encoded in color. So different color of these dots, these spheres, indicate the particular phase of the state. So if I look at this Q sphere, I see that my output state is in the superposition of two 0, 0 and 1, 1. The size of these spheres indicate the probability amplitudes. So I see that the sizes are the same, so I conclude that the amplitudes are also same in amplitude. Amplitude says yes. So the amplitude is the same. and the color indicates the phase. So these two are in the same phase. If I look now at these two guys, the state 0, 0, 1, 1, I indeed see that the amplitudes are the same, and the phase, which is given by this phase element, usually this imaginary unit here or minus here. So for this particular state, the phase is the same. If I, for example, change this one to state 1, in the initial state, right, the result of this computation is this one, and I observe this minus here. How it will be indicated in the Q-sphere? As a change in the phase. So if I run this Q-sphere representation, I see the change of the color of this state 0, 0, which is the color of phase pi. Okay, so that's how we represent two qubit system. For example, for a 3-qubit system like this circuit above, this one, okay, we also simulated this one and got this result here. So it's a 3-qubit system. And if I run this representation for a Q-sphere, I will get this. So you see, it's not only on the south and north pole, it also gets these cross sections, okay, here and here, and these cross sections are needed to represent more qubits. If I add another qubit, it will get another cross section with more qubits, more the cross sections like this. Color still indicates the phase, and the size indicates the probability amplitudes. All right. Also, Qiskit allows you to represent an entire circuit in an operator form. For example, here, golden quantum circuit. This circuit with Hadamard gate, CX gate, and so on, I can represent in an operator form, just calling for this function operator, and then the name of the circuit, okay, and then it returns this matrix, which represents the quantum circuit in a operator matrix form. In your third homework, by the way, you have some assignments to convert the circuit into operator matrix form. For this, you can use either SymPy Quantum or Qiskit. The result is the same. So that's up to you. So next important concept, like say a subsection, is so-called Greenberg-Horn-Zeilinger state, or simply GHZ state. It's very easy to recall because for me, from microwave physics, it looks like a gigahertz, right? So GHZ state. So what is GHZ state? GHZ state is a generalization of a 2-qubit circuit, 2-qubit golden circuit, to the case of to a system of n qubits. Okay, for example, 3 qubits or 4 qubits. And this is a circuit for 3 qubits. Okay, you have 3 qubits, and then you create the first one in the superposition, you prepare the first one in the superposition, and then you connect the rest of the qubits by their neighbors, right? By pair, using the CX gate. And let us let us calculate the circuit and see what's the result. So I create a 3-qubit circuit, add the Hadamard gate to the first one, to the 0-qubit, then Cx between 0 and 1, and then another Cx between 1 and 2. I draw the circuit. I create a state vector 0, 0, 0, okay, 2 to the power of 3 because we have 3 qubits, and I evolve the circuit to get the final state, and I represent this final state here. And what's the result? The result is here. So this is input state, this is output state. So as you can see, it is exactly like Bell state, but we added just one state here, right? We added just 1 qubit. So it is a perfect superposition of 3 qubits. Again, completely inseparable state, but it bears name of these 3 gentlemen, Greenberg, Horn, Zillinger. GHZ state. So GHZ state is generalization of the Bell states to multi-qubit systems. Very important, and yeah, important concept. Again, if you measure any of these qubits, for example, you measure second qubit, okay, and let's say you got the second qubit in a state 0, then this final state, immediately collapses to just one term, this one, and you conclude that the qubit 0 and qubit 3, or qubit 2, sorry, are in the state 0, and you cannot find them in state 1. So it will be their functions will collapse to the state 0, regardless of physical distance between the qubits. Very nice. Yeah, and this state is indicated like this. The GHZ with index 3, for example, like in this case it's 3. GHZ with index 2 is a Bell state. Measurements. So I encourage you to read all this. So basically, the quantum circuit in reality cannot be just a circuit. It must end by measuring gate, okay, or measuring operation. So we need to add measurement in the circuit in order to make use of the quantum circuit. And the way we add the measurement, we also create a classical register, because the information from quantum register after measurement must go to a classical register. Okay, so I do this here. So you just use the same function, quantum circuit. This is the number of qubits, and this is the number of digits in the classical register. Okay. Yeah, for it can be changed. For example, 1 or even 0. So it's just 0. Okay, it must be 1, I guess. No, something wrong. Index 1 is out of range for size 1. Okay, yeah, because I use these operations here when I measure, so I need to use 3 here. Anyways, so again, yeah, so I create the same GHZ circuit, then add the non-physical barrier. Is just the line like this, so it basically it divides two parts of the circuit, right? It can be It's just for us, so it's a artificial, arbitrary barrier. And then we add this measure gate this way. So I simply put this measure gate for all 3 qubits. This is the range 3 here, and this measurement returns the information to the classical register, to all of them, to all 3 classical registers. Let me change this one to 1, and this one is 1. So I guess still nothing. Range must be fall 3 to 1. Barrier. Interesting. Okay, anyways. Alright, so yeah, so this is the circuit with the measurement part. Okay, and when you see this element like this, it means measurements, and after the measurement, the quantum state of the circuit, of the entire circuit, collapses to some other quantum states or even to classical states. Okay, and yeah, this is how we retrieve information from the quantum circuit. Drink some water. All right, so one popular simulator is called QASM simulator. This QASM simulator can be executed on the remote backend at the IBM part or on your computer. Okay, and the number of qubits here is restricted by a number 32. Why so? Because 32 qubits is already big number for a classical machine to execute. 32 qubits means that the number of amplitudes in of the quantum states will be given by 2 to the power of 32 elements. Okay, and all vectors will be given by 2 to the power 32 elements, which is a very large number. You cannot even compute such vectors. And the matrices will contain 2 to the power of 32 times 2 to the power of 32 elements, right? Because any matrix is square matrix is 2 to the power of 32 columns and the same number of rows. So it's a huge number. That's why typically we don't simulate using a quantum simulator or simulator a quantum computer approach more than 32 qubits. Something like 50 qubits still can be simulated using a supercomputer, like Google in the past simulated this, or they simulate the quantum computers of 50 qubits, but using like state-of-the-art supercomputers, just 50 qubits. In contrast, like for example, for comparison, today we have quantum computers with 1,000 qubits. So we have already machines that cannot be, even potentially cannot be simulated using classical computers. Yeah, so for such kind of calculations, simulations, we use QASM simulator. You can read more about what is QASM simulator what kind of functionality it provides more. So here I'm just giving you an idea how it can be used. And so basically, caster simulator, in contrast to execution here, evolve. So this evolve just evolves the perfect quantum circuit like this one. If you need to add measurement, and measurement also brings noise, inaccuracy, etc. So all that can be taken into account using this custom simulator. So measurement, noise, imperfectness of a quantum computer can be taken into account using this custom simulator. So this is a simulator of a quantum computer the way it would operate in reality, okay? And you can control this noise and other parameters. Anyways, so this is how it works. So you, of course, need to import this AR simulator. Then and you also need to you need to use this function transpile. Okay, I will explain what it means. Transpile. In short, transpile means you have a circuit and you transpile the circuit into a more feasible form. Okay, and feasible here means either is it easier to simulate or doable by a particular system. Okay, so transpile this operation. Okay, to be able to use this simulator, I call for this simulator. Okay, so I write this AR simulator and give it a name, backend. So this is my backend. Backend is basically a machine that I will use to simulate the circuit. So this is my backend now. I don't call for IBM machines, IBM servers, so it's still totally on my local computer for now. Okay, so first I need to transpile the circuit. I take my circuit above, this one. Okay, so this is the circuit that generates this GHZ state, but I also add this measurement here. And as a first step, I try to transpile the circuit. Okay, so I write transpile, then the name of the circuit, then my backend, which is this guy, AR simulator. Because the purpose of this transpile, as I said, is to change the circuit, reconfigure it in a way that a particular backend can simulate. Okay, and then I give it a name, a new circuit. This new circuit is named GHZ compiled. Okay, it doesn't really matter. a new circuit, and I draw it, and this is the result. So you can compare; it's exactly the same circuit. This is because such a simple circuit doesn't need to be transpiled to be executed by this backend, which is AR simulator. Okay, if I would have a more complicated circuit, or if I would have another backend, as we will see today, this circuit will be changed, but changed in a way that it does exactly the same operation, but more feasible to simulate on a particular backend. Okay, and then we need to run the simulation. So we basically called for backend, apply run, the name of the particular circuit, and give it a name, give it a number of shots. Shots are the number of runs, like repetitions. So I prepare the circuit, run it, measure, prepare, run, measure, and I do this 1022 times, which is by default. Okay, but I can change this number. I run it, and it's done. So it's very quick. This simulation is very simple. Then I need to retrieve the results. So from this, I give it a name. I give a name to this simulation result, right? Or this operation, or this job, actually. And then I call this job and write dot results to get the results. And I give it a name, GHZ result simulation. Okay, so this is the results. And I plot, and I need to say what kind of results I need, because different backends, they produce the result in different form. Okay, so the result is a number of counts. The result can be a state of a final qubit. The result can be a Q-sphere, something else. So here I specifically tell that I need the counts. The counts in this case will be the number of the results of measurements. Okay, so I get the counts, and then, for example, using this plot histogram, which I also import, I can represent the results. So this is the result of this experiment, and as you can see, in result I get only two states, 0, 0, 0 and 1, 1, 1, as expected, because let me go to the quantum simulation here, right? So this was the state 0, 0, 0, this is 1, 1, 1, and no other states here. And more or less 50% probability of getting 0, 0, 0, and 50% probability of 1, 1, 1. So in a perfect case, in a perfect regime or scenario, these two numbers must be the same. But this solver brings some amount of inaccuracy and noise to mimic this imperfectness of a quantum computer. Okay, so this is the result. I can run the simulation once again and get other numbers here, of course. Okay, so these are other numbers. I can change this number of shots, and for example, if I make just 10 runs, because of the internal randomness, right, of the circuit, the result is stochastic, it's probabilistic, and this can cause a large dispersion, right? This very drastic difference comparing to the perfect case. In perfect case, it could be 50-50, but the less number of shots reveals this this randomness in the simulation. However, if I increase this number, this alternation from the mean value, okay, will be much smaller, like this. Okay, so now it's completely almost the same numbers comparing to the total. All right, so this is the simulation of our system on our computer. Let me dd this one. Okay. So now let us transit to the next to another golden circuit, which I call single qubit circuit. Single qubit golden circuit. And the more official name is Ramsey interferometer. Okay. So now this circuit is simpler. But also very important to understand the idea here. In contrast to two-qubit circuit, two-qubit golden circuit, which creates entanglement. Okay, entanglement. Single-qubit golden circuit creates superposition. Not superposition, but interference. Okay, interference of quantum states, which is another component of a quantum computer. Okay, so this one creates interference. So the golden single qubit circuit looks like this. So we have one single qubit, of course. And then we create a superposition of this qubit in state 0 and 1. Then we have some phase gate. So in this case, it's pi over 2 gate. And then we close this state by applying another Hadamard gate. And then measure the circuit. This is how it works. We can vary the phase of the phase gate. For example, now I make it pi. Okay, it can be 2 pi, whatever. It can be any phase you like, you want. Let me make it back over 2. Okay, and yeah, now using exactly the same procedure. I just changed this name, Ramsey. Okay, so this exactly the same procedure. I run this circuit, and this is my result. Okay, so I see that. Let me actually increase this number so we see that like this effect like more perfect. Of course, in the result I can get either 0 or 1, right? And from this simulation, I see that for this particular phase, the output state of the circuit is 50-50, is 50% in 0, 50% in 1. Okay, so it's like quantum dice, right? This game, you get either one side or another side on a randomly. However, if I change this phase and, for example, make it pi, okay, the circuit is the same, but I change this phase to pi, and I run this simulation, and I get perfectly 10,024 counts that hits state 1. Okay, so I change phase and it creates change the probability of the result. Let me change this phase, for example, to 0. So 0 phase. What would I get? It's very easy to expect that I get state 0. Okay, so also probably in your homework, but anyway, it's very easy to see from this circuit. So the phase gate with 0 phase is the same as like I would have nothing here between these two Hadamard gates, right? So just nothing here. At the same time, since Hadamard gate, this H gate, is a unitary operator, and if you apply unitary operator twice, you get the same, you get the state before. So the same operator applied twice cancel each other. And in the result, we get just state 0 because this initial qubit was prepared in the state 0 before the experiment. And so on. If I add this another phase, for example, over 3, pi over 3, that's another state, pi over 4, another distribution, and so on. So changing the phase of this gate, of this phase gate between two Hadamard gates changes the probability distribution of measuring this circuit. And in fact, and you can watch this video above, this lecture 9 of my previous course. This distribution, this dependence of phase is given by sine squared function of phi, sine squared. Okay, so it changes from 0 to 1 and back to 0 as a sine squared. Yeah, and as I said, this is important circuit because this is how we create interference. You probably know that, like, if you have one beam of light and another beam of light, and if these two beams are coherent, for example, made from the same light source, and you superimpose them, where in the places where the field comes in phase, the field increases itself, right? In the places where the field comes in opposite phase, is minus in phase, the field cancel each other, so you get 0, and as a result you get this interference pattern in such an experiment. So exactly the same happens here. So this Hadamard gate creates a superposition, or in this optical analogy, it creates two light beams. Then this phase element adds another extra phase to the second light beam in this light analogy. Okay, and then this second Hadamard gate works as a screen. So it overimposes two light beams, and it creates superposition, or it creates interference. And interference created by a circuit like this, and entanglement created by a circuit like this are two important components of any quantum computing. Okay, a quantum computer must have both interference and entanglement. Okie dokie, and now, so if we transit to the real quantum computer, okay, so a real quantum computer calculation of a single golden circuit, right? One golden circuit. All right. So in order to send your work to one of these IBM quantum computers, you first need to import IBM provider. So this is IBM provider, and then you need to use your token to connect to your account. Okay, so you have, when you register, yourself in the system, you get a space on their memory. You basically get a account with memory and so on. And using this token, which is IP token, can be found where it can be found on your account. So if you go to platform here, so when you get to the so by the way, do you see my screen now as I changed it?
Yes, I see.
Awesome. Yeah, so this is the IP token. And if needed, you can change it, refresh it, as I will do after this lecture. And this is my particular personal IP token. So you write IBM provider save account, and then use this. And I also recommend to write this override true, so it doesn't conflict with itself when you run it multiple times. Okay, so then this is your provider, and so Qiskit is written in a way that provider can be different. Okay, today we use IBM provider, but provider can be, for example, a Google, and you can connect to Google using the same approach. But for now, here we use only IBM, so I write IBM provider and give it a name provider. So this is my provider. Using this name provider, I can, for example, call for a list of available backends. Okay, so this is the operation. So basically, available cloud backends, provider backends, and it basically prints the list. Here is the result. So all backends with this word simulator means that this is not a real quantum computer, it's just a simulator of a quantum computer. What else here? Simulator. Yeah, and the machines without this word simulator, like these three, are real quantum computers available for you right now. I really like this function, because if you go to IBM Quantum and to the list of available machines, which I get, for example, oh yeah, I need to log in once again. Give me a second. I will do control. Intercode. Where it was? Let's change this. Use email. Yeah, I received the email. Use this code. Verify. Okay, verified. Yeah, here's my point. If you look at all systems, you will see a much larger list of quantum machines. And some of them can look even more. Oh, they are pretty much the same. They remove this small number of qubits machines. Yeah. So this these simulators here and the quantum machines over here, unfortunately, the most of them are not available for free today. Okay, and only, for example, right now, only these free are available for these teaching purposes and maybe research for free. All right, so we don't need to pay for using a real quantum machine. How cool is that? All right, so for example, for this one, I already conducted these simulations today and several times actually. It's not predictable. It takes, for example, today one simulation required about like 1 hour or so. It was in line for about 1 hour. But another simulation took just maybe 1 minute, and the time is for you like in the line, because there are a lot of other people who want to use this machine. The simulation itself lasts maybe 1 second or so, 1 or 2 seconds, and the most of this time is because we run the circuit 1,000 times. Okay, the simulation, the single shot simulation of a circuit like this can take even like a few microsecond, I think, few microsecond. All right, so I choose the particular backend, and in this case it was IBM Brisbane. You can alternatively use Kyoto or Osaka. I think these two located in Japan. There is a IBM Japan, so you send your project to Japan, Japanese quantum computer. Again, this is the circuit, very exactly the same thing. And then first, before sending the circuit to your backend, which I called QComp, it is quantum computer QComp. So this is the backend QComp. This is the name of the circuit, which is Ramsey, and I transpile it. Okay, so in this case, this transpiled qubit, which I draw here, looks like this. So it contains this all 126 qubits. You see, but all of them are not used. So I use only the qubit 0. And for the particular phase, pi over 2, the qubit, or Qiskit, transpiles this circuit into this one, the square root of x. That's it. So basically, what Qiskit says is that this circuit is not it can be transpiled, it can be simplified to the use just one square root of x gate. And square root of x, by the way, we didn't discuss, but it's straightforward. It's just 2 square root x gates placed in series creates one x gate. So square root of x is not unitary, but square of square root x gate is unitary. Okay. Yeah. So this operation, this function transpiles this circuit to be executed for the quantum machine. So it simplifies, it makes the simulation more feasible. For our case of free gates, it's not even needed. However, if your circuit contains hundreds or thousands of gates, it's very, very useful to transpile it first, so it simplifies the things so that it can be computed on a quantum machine. Okay, And then there is a standard procedure. There is a function run here. So I call this. So this is my circuit transpiled, right? No, qcomp. This is initial. This is this is sorry. This is this is the backend. Sorry, yeah, this is the backend. So you call this backend apply function or method run, and here you indicate the circuit, this transpiled circuit, transpiled after this operation. Yeah, and when you run this line, your system, your computer connects to the IBM server, sends the job to the IBM quantum computer. Let me run actually this. So you see that if I go to my IBM quantum platform, I immediately get this. You see this less than 1 minute. So this is the project I just sent to the IBM quantum, and you can see this name of the backend, which is IBM Brisbane, number of shots 4000, the time when I created this, the job ID. So this is the unique name of your execution of your program, right? Yeah, and this circuit is sent to be executed on a real quantum machine. So for now it's in line with it, but at some point, maybe in few, it can take from few minutes up to few hours, and this waiting time is random, so you never can say. But in a couple of hours, for sure, you get the result. And when you see that your job is executed or completed, it will be green here. This indicator that the job is completed. You can download the results. Okay, so you create this line results. The job Ramsey. This is the name of our job. In this Jupyter notebook file, and then dot results. So this is a method that retrieves the results from the IBM backend. Okay, and then I plot the results. So these are results from execution of this circuit from a real quantum computer for the phase pi over 2. So let me go back here and change it back to now I can't compute because now it's no, I can. Okay, pi over 2. Okay, you see that this is the result. Let me actually start even earlier. No, I don't have that one. Anyway, so this is the simulation result from the quantum computer simulator with some amount of noise. Okay, so this is the result from computer simulator, not a real quantum computer, but it's a virtual machine. But this result here is the result from real quantum computer, and you probably can notice some like more level of noise, and in perfect case it must be perfect 50-50%, because for pi over 2 we get 50-50 distribution of the result of the measurement. The quantum computer, of course, has some amount of inaccuracy, and that leads to this result. This mismatch with a perfect theoretical prediction of the result. But still, the result is very nice. So this discrepancy is considered to be like negligible for this one. By the way, what kind of computer we use? IBM Brisbane. So if I go to this IBM Quantum and go to this machines, oh yeah, this is one. This is the one, IBM Brisbane. So this is a part of so-called Eagle processor. Okay, so IBM named their processors after these birds. So this one is particularly Eagle processor, and you can look at the topology of this processor that we used right now, and this processor contains 122nd qubits. Probably one is damaged, right? This one is no. Yeah, this one considered to be like a little bit noisier than others. This one, anyways. And there are some other parameters. You can see what kind of computer is that. You can Google for this computer, this Eagle quantum machine, and look at the picture of the quantum computer you just used. Also, you can check this T1, T2 times. I recall this is the decay time and dephasing time, very important parameters. So your one run of your circuit must be less than this time, otherwise you can't run your circuit. I mean, more or less. Yeah, and this is the result. And very quickly, because we run out of time, the simulation of 2-qubit golden gate, the golden circuit. Why golden gate? Golden Gate, the name of the bridge. Circuit, of course. Circuit. Conducted in exactly the same way. I use here the same backend, create a circuit, check that the circuit looks just exactly what I want. Then I transpile the circuit, and this is how it looks like on a computer that I'm gonna use. You see that now I started from this circuit, which looks just, I mean, very simple, right? It's just Hadamard and then C naught. Still, this transpile function transpiles the circuit to a circuit like this, which with much more like number of gates. Why? Because this particular backend, IBM Brisbane, cannot simulate a circuit like this. It must it must prepare the circuit in a form that it can simulate it. Okay, so this is exactly a circuit like this, but prepared in another form. Important point about this one is that this is already a circuit that creates superposition of states. And this is the result of quantum simulation. Again, we get state 0, state 1 with 50% probability. But this more, yeah. So this is the result. You can find these works in jobs here, over here, right? So this is supposed to be the one. Yeah. So this is the circuit we created here. So this is not the result. This is from something else. This is from another job, I guess. So this circuit over here, okay, I send it for the simulation with the same procedure as above. And this is the circuit, this exactly the same circuit, exactly the same machine. And this is the result of simulation. You see that in this simulation of this circuit, which is, by the way, I remind you, creates a Bell state, state 0, 0 plus state 1, 1, right? The result is this: state 0, 0, state 1, 1, and some little contribution from states 0, 1, 1, 0. So in perfect case, we would have just two states, 0, 0, 1, 1. And if you run a quantum simulator, the simulator of a quantum computer, you would still get state 0, 0, state 1, 1 without these states in the middle. Real quantum computer also creates these states in the middle, which are considered to be inaccuracy. Okay, so this Bell state 2-qubit single 2-qubit golden quantum circuit is a circuit we use to test, to benchmark the quantum computer. Okay, yeah, and this particular one is very, very nice. This contribution from these states is very small. Yes. This is also a nice indication or nice example of the result we get from quantum computer. We never get yes or no result. The result is always probabilistic. Okay, so from this picture I see that, okay, the probability of getting this state is much, like maybe 20 times larger than probability of this one. But still this result is not zero. Yeah, and we have to take into account or figure out how to, if for example this would be larger, we need to find a way how to get rid of these results. One way is to increase the number of shots. If I increase the number of shots, the difference between the correct result and incorrect result increases. Okay, and yeah, maybe the last point to mention that, okay, this is 1000 runs of the same circuit, the same quantum computer. However, we have a number of quantum algorithms that work in one single shot. So we don't need to run computer thousands of times. We just need to run it once to get a right result. For example, this Grover's algorithm, it runs in one run. Okay, this is just one example. So yeah, this is all what I wanted to discuss today. In your lab work, you will basically need to repeat this quantum simulation of a circuit that you will find in your lab work assignment. So thank you very much, and let me stop the recording.